Hello, everyone. Welcome to the second session of our fall 2024 program for the Virtual Inter-University Symposium on Infrastructure Management. For those who are new to VISIM, it is a virtual symposium that is hosted by Professor Pablo Durango-Cohen here at Northwestern University. Today, Alireza and Manuel will be presenting their work. Each presentation should be about 20 minutes long, after which we'll take questions from the audience. Please feel free to speak your questions or send them using the chat feature. The meeting is being recorded and will be made available shortly after. Thank you, everyone, for attending. All right. The first presentation is from Alireza. Alireza holds a PhD in Industrial and Systems Engineering from the University of Oklahoma, where he was awarded the Best Dissertation Award for his research on game theoretic algorithms for decentralized decision-making. He also holds a master's degree in industrial engineering and a bachelor's degree in industrial engineering from Azad University in Iran. After completing his graduate studies in 2023, he has focused on advancing methodologies in dynamic, interdependent network modeling, particularly in risk assessment and infrastructure resilience. And he is currently a postdoctoral scholar at Vanderbilt, where he's developing frameworks to identify interdependencies among critical infrastructure networks and assessing vulnerabilities in road networks. So I'd like to hand it off to Alireza to start his presentation.
Hello, everyone. So let me just share my screen. Okay, so everyone see my screen? Okay, so my name is Alireza, and today I'm going to speak about anticipating uncertain infrastructure interdependencies, a case study of coupled power transportation network. So we have our interdependent infrastructure networks highly interconnected with each other, and this interconnectedness, high interconnectedness, are in fact the source of efficiency that we see in our systems. But these highly interconnectedness is in fact also increase the vulnerability of our system, as disruption in one part of the component can easily propagate through the system. Now, recognizing these interdependencies are very much important when we wanted to do some risk management, resilience planning, or also resource allocation. So many of these interdependencies are easy to realize. For example, if we have a physical interdependencies, we can see them, but many of them cannot be realized easily because it is pretty much related to the functionality of the functional interdependency, some logical interdependency, different characteristics. So this is all because of having different dynamic and uncertain network behavior. We can see dynamic and uncertain network behavior, which these interdependencies can change through the time. So considering this, our first and primary objective of this research is to evaluate how disruption failures or components can affect the failure of the other components. So explicitly defining this objective, we are going to create a bipartite weighted graph where each vertices of this network or this graph is going to be the functionality status of certain node in time t-1 and time t, or the current time. And the weights for each link denotes for the failure propagation probability from one component in previous time to the other components at time t. So, and then using this probability and this net graph, we can see how these disruption propagation can evolve through the network during the time. So the problem that we have, the topology data of these networks are pretty much available. But with respect to the interdependent network disruption data, which gives us a dynamic disruption of the network through the time, it's not easy to find. And it is pretty much difficult to come by those data. So what we are going to do is to define another objective, which is to create a discrete event simulation model that can illustrate the interaction between these networks. Can illustrate the interaction between these interdependent infrastructure networks. Now, this simulation that we've done is pretty much considering the interaction between the power and road network, and also with respect to the road network, we have considered congestions, accidents, features like congestion, accidents, road capacity, and also the spillback. For the supply, for the power network, we consider the supply-demand equilibrium, and also we consider that the repair crews who are responsible for restoring the disrupted component are going to use are dependent to use to the road network so that they can reach to the disrupted area in order to repair the disrupted component. So at the end, what we are looking for is this matrix, which each element of this matrix shows the functionality status of each component at every time or every time interval. So then, okay, let's have some definition here. So we have direct initial impact. So the power or road component can be independently affected by external event like natural hazard. And also we need some repair crews to go and just repair these direct initial impacts. And these repair crews are dependent on the road network to reach their destination. Now, as a result of these direct initial impact, we're going to have some indirect impact. So, for example, disruption, if we have some disrupted links, so we can anticipate that we are going to have higher congestion in the system, and also the risk of accident will be increased. With respect to the power indirect impact, power network, we in all the time we need to keep this equilibrium between supply and between supply of the power and also the demand of the power. So and then these indirect recoveries, especially in the road network, is going to be these indirect impact, I mean, are going to be temporary, and it's going to be recovered in certain time. And also for the power network, these repairing the directly affected component can restore the failed one, which has been failed just as a result of the direct initial impact. So with respect to the interdependency, we define a geographical interdependencies, which each node or each power component is going to be tied to a certain location, and the correspondent component in that the correspondent component in the road network is going to be disrupted if, for example, that certain power node is going to be disrupted. We have this, for example, if we have a power pole falling on the road and just block the road and then needed to be fixed, so that the road corresponding to that power pole is going to be disrupted as well. Also, we have functional interdependency, which a power component failure cause failure in traffic lights, and then we are going to lose some visibility in the certain district, so the risk of accident will be increased. So this is the general flowchart of the simulation model. At the beginning, we are going to introduce the vehicles into the system, and considering them and calculating different features, the movements, the paths, the speed of the vehicles in each link. Then after the warming up period of the simulation, we are going to consider the initial impacts or the natural hazard. As a result of that, we are going to find and after that we are going to capture the power network functionality, considering that these equilibrium between power and between supply and demand should be maintained. And then after that, we are going to calculate the indirect impacts on traffic or the road network. Then we're going to consider the recovery procedure of the network. We consider that the road accident caused a temporary blockage and will be resolved after certain areas, and also repair crews respond to initial direct disruption navigating through the traffic network. This was okay. So for the power optimization, for the power supply and demand equilibrium, we have this, we consider this optimization model. So the first objective of this optimization model is to provide power to all demand node as most as possible in every point in time. Also, unmet demand leads to failure in power network and associated link in the road network. And then we have a different set of coefficients. So the first part is just for maintaining the balance between the components of the power network. For example, if we have the supply nodes, demand nodes, and also transshipment nodes. And the second part is the if we cannot, is to make sure that if we cannot provide enough supply for certain demand node, that node needed to get that node needed to be failed or needed to be get offline. And after that, but the supply nodes can in fact adjust their supply to a certain limit. If the demand in the system decreased to that certain limit, decreased more than a certain limit, they needed to also get offline, so that we are not going to supply more power that it is needed to the system. So this was the optimization model that is going to be solved in each iteration of the simulation, so that we can see what is the situation of the power network. Now, for example, this is a power network example that we have here. For example, this is the situation of the network at the beginning. Now, for example, these are the nodes which are directly impacted, and as a result of these impacts, we're going to have these nodes in the power network which indirectly impacted as a result of those direct impact as directly impacted components. Now, for the road network, we can define different resiliency metrics, but this is one of the resiliency metrics that we define. So, which is related to the speed of vehicles in our system. So we have a maximum ideal speed in each links. So as a result of congestion, this speed will be diminished. What we are looking here is that we wanted to calculate the deviation between the maximum and actual speed at each road segment to measure and use it as a measure of the road network resilience. So we can do this for each links in the road network, and then we can make an average average for all of the links at each time interval, so that we can come up with this diagram at the left. So at the beginning point, we have the ideal resilience when we don't have any car in the system. After the introduction of the cars or vehicles into the system, we can see that the resilience dropped and come to a kind of steady state level. Then after the warming of the simulation, we introduced the initial impact, and then you can see that the resilience of the road network dropped to a certain amount, and after the recovering of the system, we can see that the system the network resilience rebound back. So, and then when we make an average over the whole time or the time horizon of the that we consider, we can have the same resiliency for the for different disruption treatments. For example, we have different levels of disruption in roads and power, and then the result that we can, and then we found this response surface for that, and then as a the takeaway that we can have from this response surface is that initial power disruption ratio have minimal impact on road network resilience unless the road network ratio increase. I can say simply that the road network resist to some amount. So we can say that if the road network hasn't been disrupted a lot, disruption in power network doesn't have a lot of effect on the road network. But when we have high disruption in road network, we can see that the power disruption or disruption in power network also affect more on the road network. So it is evident with this slope that you can see when we have low disruption ratio for the we have a low disruption ratio for the road. The slope, the relation is not pretty much significant. But when we have high disruption in ratio in road, we see that the resiliency drops more. We can see this slope here. Now that we've done our simulation model, we wanted to get back into our primary objective. So the goal here is to determine if the component, for example, A, will be impacted at time t. All right, given that we have the information of the information with respect to the functional status of each component and at time t-1 or previous time. So the objective is that we wanted to see that if this component is going to be, this certain component is going to be disrupted or not. So we define a variable or a target variable representing the functionality status of that component, and then we have the as an input we have the functionality status of the other components at time t-1. So considering this, we have this data configuration, which we have our features and also our target network, our target variable. Then everything is ready for doing some sort of, after preparing the data, we have everything ready for doing some sort of machine learning. So here we use the logistic regression, and then and then this logistic regression gives us a kind of regression function, and then utilizing the coefficients related to that regression function for each of those features or each of those variables, we can come by with some sort of propagation probability of disruption propagation probability of having different disrupted component in time t-1 or the previous time, and then see what will be happen, or and then see their contribution to the disruption of our target network, our target component. Now, these coefficients can be positive or negative. Using this positive and negative functions, we can come by and then using these coefficients, we can use this formulation in order to calculate the probability to see how these combinations of the components, the functionality status of the component at t-1 is going to affect the disruption of certain component in the current time. So for doing this, we just gathered the data from our simulation model. Then we balance the data, and then we've done the feature selection because the matrix is pretty much large. We had columns. The number of features that we had at the beginning was was equal to the number of all components that we have in our network. Therefore, we use the regularizations, regularization, and then I've done the cross-validation, and then only keep the significant models which had the accuracy or cross-validation more than 60%. Using this model, using this methodology, we found 150 components which had the cross-validation score. We find more than 150 relationships. We found more than 150 components that had relationship with the other component in the network, which had the cross-validation score more than 60%. Now, using these probabilities, this was the disruption propagation through the network. Through the road network. So the yellow one are the initial disruption, and then you can see the red disruption, the disruption propagate considering the time, and then this would be this situation of the network in different time. So the conclusion of this work is that we use the simulation model is to, in fact, realize the interaction between the power and also the road network. And also we use the machine learning model and also the logistic regression, and using those coefficients in order to capture these relationship between this relationship between the disruption of one component to the other components. Thank you very much this was the end of my presentation. Thank you very much for hearing it, and thanks for the opportunity.
Yeah, thank you so much. That was really great. I'll open it up to everyone else if anyone has any questions.
I'll ask a little question, unless someone else has questions. But so I think it's nice to capture these interdependencies across systems as you have. The one question that not a question, but so much as a comment, it seems that particularly when we're talking about power and transportation, that it might be interesting to capture these interdependencies, not only when there are disruptions, but even for ordinary operations, right? And so, for example, as we are transitioning to electric vehicles and so on, one would imagine that these interactions are only growing stronger, and so that's a comment that I wanted to make. As far as the question, I am curious what types of disruptions you had in mind. I mean, I think that like kind of beyond the example that you gave, which was the pole falling, right? This didn't seem very intricate, and so I was curious if you had other example interactions and disruptions that you were taking into account.
The disruption that I consider from the power to the okay, so I have defined two type of interdependencies, okay, in between the power and also the road network. One of them is the geographical interdependency, which was, I mean, falling a pole could be only one example, all right? Anything could be happen. For example, cutting the wires, or well, for any reason that we can see that, for example, one component in power network is going to disrupt it, and this disruption with a certain probability, I consider a certain probability as well, it's going to propagate through the road network. Although when for example, when the crews, repair crews get into the road, they will block the road because they wanted to fix uh, uh, the power node which has been disrupted. So that also should be considered. So the road, if the road is not disrupted, yet still, for example, car can pass through, but when the repair crew gets there, they disrupt that road so that they can do their own job. So these, I also consider this one. The other one was the other type of the disruption that I have considered was the indirect one. I mean, just for example, if we have proper lighting in the system, in the road network, because of disruption in certain power node, so that, for example, a road district is going to be disrupted. And as a result of that, the visibility will decrease so that we consider that a higher rate of accidents in these areas. But I have to say, we can add a lot more features to this simulation. But I mean, this wasn't in the scope of this project, but definitely we can make it more realistic.
I had a quick
Thanks.
follow-up to that question. Did you consider the power network impacting the traffic signals going down?
No, that's one of them.
Okay,
I didn't.
gotcha. All right, and
So
then
that's interesting. I think that also if the power goes, like you may not be able to pump fuel into cars at gas stations. I mean, there does seem to be many interesting things that could be modeled. But let me pass it to Hossein so that he can ask his question, and then we can move on to the next topic.
Oh, perfect. Thanks. Thanks, Alireza, for your presentation. I just had a quick question on the modeling of the road network. I was wondering how much it is, or it can reflect the reality of how the road network and traffic works in the road network, because there are other ways of modeling the road network, either network theory based or agent based modeling and things like that. You chose a different approach. I was wondering how realistic it is, how much it reflects the reality of how things move in the road network.
Mhm.
You just connected roads to roads based on if they're connected to each other, which is one approach. But is there any comparison if it reflects the reality or how it is different from other approaches to modeling a road network?
Well, I can say what I've done. All right. So I have some sort of random travel demands, right? That coming in, that is pretty much something like in each iteration, we are going to have certain number of vehicles coming into the system, and also some certain number of travel demand is created using certain probability. I use the normal probability. Then and then the next objective is to find the shortest path. All right. At the beginning, the assumption that I had in my mind is that, okay, these days everyone using the Google map and finding the shortest path. All right. And whenever and then I assume that Google gives them the shortest path that they can reach. And anytime that, for example, Google find a new situation saying that, for example, they can reach to their destination faster, they give a suggestion. All right. And this is the best response of the vehicles or the drivers to opt to the new shortest path. Now, in our case, I consider that, okay, when we have the disruption, we are going to have more congestion in certain points. And then because of that, in each iteration, let's say that we have some sort of system like Google Map system, that they give suggestion to the vehicles so that they are going to change their path. So this was the assumption that I've done for the path, and also for the speed. So speed of the vehicles in each in each link, and using that speed, we can and having the position of the vehicle, we can calculate how much a vehicle can cover the road or covering its own path, considering the speed of each link, the average speed in each link. So this was almost the way that I calculate these things. I don't know if I answered your question correctly.
I know, that's good. Thanks.
All right. Well, thank you so much, Alireza. We will move on to our next presentation. All right. Manuel, please feel free to share your screen, and I will start my introduction for you. All right. Manuel Contreras is a civil engineer and master in engineering sciences from Universidad de Concepción, and currently a PhD candidate in engineering sciences at Pontificia Universidad Católica de Chile. After finishing his master's and bachelor's degree in 2018, Manuel has worked on various research projects related to risk management in road networks in the face of natural hazards, as well as on issues related to road safety. Currently, as a PhD student, he is working on the development of a risk model for landslide risk in road networks and is part of the National Research Center for the Integrated Management of Natural Disasters. So Manuel, please feel free to take it away.
Can you see my presentation on my moderator screen?
Yep, it looks good.
Okay. First of all, thank you for the invitation to the symposium. I think it's a very good opportunity to share our work and generate possible collaboration opportunities. Well, about my presentation is entitled Assessing Rainfall Induced Cut Slot Failure Probability Curves, a case of study in the rock network of southern Chile. This is part of my first part of my thesis, doctoral thesis, which I have working for some time with the professor Alondra Chamorro here in Chile. The presentation will be divided in 4 topics: the introduction, methodology, and cut slide favorability curves, and the results and ongoing works. First, with the introduction. In the context, landslides or slot failures, in this case, is a problem for road networks, causing road closures or either total or partial disruption, as shown in this image. You can see a partial and a total interruption. These problems are not only for the users of the road networks who see their trips interrupted by this failure, having to change their roads or wait until the problem is solved, but this slot failure also imply a cost to the road agencies in the road management, who have to solve the problem in the short term and also think in the long term how to avoid the recurrence of this problem. For example, in Chile, between the 2010 and the 2021, more than the 50% of the road emergencies were related to the slot failures, mainly concentrated in the southern part of Chile, on this country. Moreover, in the recent years, 42% of the 300 emergencies have been related to landslides. This is strong show that the number of emergencies has increased, which can be attributed to changes in the weather patterns, or as well as to the fact that the road network had become more and more fragmented and density, resulting in an increase of the exposure for this kind of hazard. Another important point is that this research is part of the project, this research project entitled Development and Application of the Traffic Interruption Model due to road slot failures caused by extreme weather events, in which 2 universities have part, the Pontificia Universidad Católica de Chile, where I'm doing my doctorate degree, and the Universidad de Concepción, participate at a partner institution. At the same time, institution in for example, the Highway Agency of the Ministry of the Public Works and the Associated Public-Private Partnership, they are important institutions related to the road management in Chile. This is the methodology of the research. It's divided in two modules. The first one, it has the objective to estimate the effect of the operation on the RAD network due to landslide or slot filery. And the second module is to estimate the risk of landslide of RAD network from the point of view of the increased travel time or delays, which can be applied to select the center where damage mitigation is required. The first module considers 5 stages. The first is the model, the hazard, in this case is the rainfall or the precipitation. The second is an hydromechanical analysis of the slope, which involves to estimate how the water infiltrates into the slope, how is varying the saturation degree into the slope. Then in the next step, we estimate the slope stability analysis and check if the filery occurs given a certain rainfall scenario. And on the fourth stage, the slope filery probability curve are estimated, where by interactively performing the stability analysis for different rainfall scenarios, we obtain the probability of failure this slope with a certain geometry and also type, given a certain amount of accumulated rainfall, for example. And finally, then we move to the last stage, where if the critical failure condition is complete, the degree of interruption is estimated as a function of the volume sliding onto the roadway. In the second module, four stages have the result. In the first stage is to estimate the restricted condition caused by the restricted zone in the first module, and then pardon. So it's then the traffic is simulated with a traffic accident model, and the risk is estimated as a function of the increase in the travel time. This can be applied at the same time for the resiliency and mitigation strategies. This is not part of my investigation, of my research. So in this presentation, we'll focus on the first module. As I mentioned, there have 5 stages. It's considered first the analysis of the meteorological hazard to define the storm scenarios. And the second is the slope characterization based on the field surveys, ladder surveys, and the laboratory analysis to obtain for example, the geometry, the soil type, the permeability. And then with this information, slope stability analysis is carried out, and finally the failure probability curves are estimated, and the landslide volume for these 5. The file is complete. Then for the development of the model and its validation, the road network of the southern Chile, what was used to this study is the Biobío region. I think is in this part of Chile. 2 roads with different categories were studied. The first is a class of highway with a length of 88 kilometers and on a traffic of 5,200 vehicles per day. The second is in El Sodo Concepción, is the road number 2. It's a bidirectional road with a traffic about 4,000 vehicles per day. And both roads are located in a forested area and have had fires in the recent years, which has changed the vegetation cover of the area. In the case of the road 2, for this road, we selected 3 slopes. The first slope in the road 2 have a sedimentary class of soil, as in the second slope. The second slope. And the first slope hub we select is the in-hub residual slope. The range of the height of the slope is about 10 meters to 17 meters, I think. And the inclination is 45 degrees to 16 degrees. Then the rainfall, following with the methodology, the analysis of the precipitation was performed based on the meteorological information and based on the meteorological information that's selected in this area. Then a correction, this information was corrected by the ERA 5 reanalysis, which provide information on typical duration on the total amount of rainfall per event. Then by means of the intensity, duration, and frequency curve was created. And then random storm scenarios was created with using the hub curves. And finally, we obtained the randomized scenarios for return period to 5 to 500 years. And we can see a different scenarios. For example, it's the same return period with a different pattern of rainfalls. As for the slot characterization, we realize a file survey to obtain, for example, with the resistivity electrical analysis, we obtain the soil resistivity and at the same time the water level into the slope. With a seismic geophysics analysis, we obtain the soil stiffness and a differential GPS, we obtain the geometry of this slope. And with a LiDAR survey, we obtain the geometry post-failure condition of the slope. And we realize some sampling, material sampling to work in laboratory to obtain these. So sample collected in the field where analysis to determine the mechanical and hydraulic properties. These are necessary for the simulation in the software we use is Plaxis 2D, which the hydrometeorological and hydromechanical and the slope stability was carried out. Some of these laboratory results were the slope, the failure envelope, and the soil water rotation curve. Then, with the information about the slope stability is simulated, we analyze it when the factor of safety is less than 1. This is the failure condition. You can see this video. In this video, for example, represent how the saturation is changing about for this rainfall pattern, for example. Then, for example, we have, you can see how the factor of safety varies according to the duration of the event. For example, we have different patterns, pattern 1 and father 1 and father 2, and the condition of the factor of safety less than 1 in the pattern 1 is at in this hour, and then file in the second hour. As a result of this project, this is the failure probability curve. Finally, after several models and runs of the different rainfall events, the probability curves for each slope are timed. In this case, the slope 1 and slope 2. The curve was fitted in a log normal distribution, and as a function of the total rainfall on the amount of total rainfall for these patterns. As an example to validate this curve, we use the event of the past June 9 in 2023, what this slope failure. So we can see which according to this curve implies that the probability of failure is greater than 80%. as a working in progress, I'm working to the next stage to estimate how the volume about the Valerie surface slide on the roadway. What is the distance effect of the road? For this work, we are using material point methods, but we are just getting started in this point. The idea is to obtain what is shown in this figure, but depending on the geometry and of each slope and the type of soil, where we will have different states of the environmental damage. For example, reducing velocity, blocking zones, or causing unintensive damage when the road is closed in both directions. For example, for two-way roads. Another work in progress is the extrapolation of to the network level. This involves considers more slopes, geometries, and different soil types into adapting this curve according to how this rain different part of the region, in the case the Bio region. For example, in the coastal zone, it's rain much more than in the central zone of Chile. It's on the duration of this precipitation is different. First, because we consider different type of soil. In this case, we consider silty loam soil, sandy loam soil, and clay loam soils, because we use the USDA classification because we work with agronomists, so it's better for us. This is an advance of the simulated curve for a network level. If we have, in this case, a course for a slope height of 8 meters and different inclination angles and two kind of soils. In this case, sandy loam. This is the curve, and for silty loam, this is are the curves. This is more. So it was found some conclusion in this work. This was found that the wall of the duration of the storm that triggered the fall is variable, and the fall but the fall bottom is fairly stable. The critical issue is to have a good estimate on the saturation level of the slope. It is really important to simulate the hydromechanical behavior of the slope. And we are generalizing the result using geometrical and soil texture data to generate maps and estimate of the propensity for traffic disruption is coupled in the road networks. So this was my presentation. Thank you.
Thank you so much for the presentation. I will open it up for questions.
I have a question, Manuel. And so I don't know if you are actually, or you envision looking at essentially all of these failure points throughout a highway, or and I think that ultimately my question is, I don't know what possibility there is to use advanced technologies to collect data, I guess, more efficiently to really decide where might it be that we want to intervene and like kind of either to put some sort of material over the fault point, protect the road. So for example, you talked about using LiDAR and you said to assess the geometry. I don't know if assessing the materials, which you also discussed, if this is possible with some automated technologies. I mean, I'm curious what we can do to kind of replicate this easily for many locations.
Yes, we are working on that. In Chile, we don't have a slope inventory about this when it's located, this slope. We have only, for this case, we selected only 3 slopes, but in the road network, we have a lot of geometries and type of slope. So this simulation are really, how can I say, is specific for this one slope. So we are thinking now to integrate for example, a GoPro in a vehicle and different GoPro to estimate for example, a 3D model of the slope in the road networks.
So image processing, this is a promising
Yes.
approach. I see. That's cool. I mean, I assume basically this might help to prioritize where you might like kind of take action.
Yes. At the same time, we don't consider other effects of the rainfall, for example, the erosion process. Now we are thinking to add in the modelation, but it's really difficult. True.
I think that this is kind of along the same lines as Pablo's question. I was wondering if the locations that were chosen to study had a known history of landslides, that you knew how much they were impacted or how frequently.
The study area is really frequent to have a landslide. For example, in this year, in August, in the row number 2, we have a lot, about 20 slope filories, and the road was disrupted about 2 weeks or 3 weeks. We're closed for 3 weeks. And this is an important road for this zone.
And is that data kept? Like, is there like a database that tracks these failures?
Yes, we have a database. Is public in database with the Ministry of Public Works in Chile.
That's great. Thank you.
And so in the results that you showed us, there was some label that was like, I don't know, let's say 5 years, 100 years. And so I don't know if you meant in terms of the rainfall and essentially what amount of rain, like if for example, a given amount of rainfall would be like kind of something that would be expected in five years or 100 years, or I wasn't sure what those years meant, or if this was like kind of the expected time until failure of that at that location.
This was the return period of this rainfall. We simulate we obtain hydrometeorical data for all the region and estimate this amount of total rainfall for these return periods, and with different duration of rainfall and different intensities. Other questions?
Thanks, Alireza. Thanks, Manuel. Please send our regards to Hiba and to Alondra.
Thank you so much.
Thank you.
Thank you for presenting.
Thank you both.